All right, next up, we'll take a look at cycloalkanes. Remember here, we're talking about alkanes. And so we're talking all about carbon-carbon single bonds. And that cyclo, it just means that it's cyclic. If carbon has all single bonds and no charges, that means that it's an sp3 hybridized carbon. And if it's an sp3 hybridized carbon, it is tetrahedral. And if it's tetrahedral, it will have a bond angle of 109.5 degrees. And so let's take a look at some of these cycloalkanes, maybe like cyclopropane, right? 3 carbons, it makes a triangle. If you think about, right, all these would be the same length side, so it's, I think, equilateral triangle. Not 100% sure on that. If you think about the bond angles here, they would be 60 degrees, right? That's quite far away from 109.5 degrees. So by putting it in this cycloalkane, we are forcing the bond angle to be different than what it optimally is. And this is called ring strain. So ring strain is basically forcing bond angles to be different than what they are or what they should be. And so if you think about the different rings we can have like a cyclopentane, right? That might look like a hexagon or a pentagon, my bad. And these bond angles would be 108 degrees. And then if you think about like a cyclohexane, this bond angle here would be 120 degrees. And so back in the day, they did some kind of thought experiments, and they said this cyclopentane should have almost 0 strain. And this cyclohexane should have more strain because it's further away from the optimal 109.5 degrees. And so, of course, in science, you make a hypothesis, then you do some experiments. And so we can get the information here, how much ring strain we have by basically burning these compounds and then measuring the energy released relative to their straight chain counterparts. And so this is the real data, right? So we can see ring size here, 3 and 4. They indeed do have lots and lots of strain. And as predicted, 5, right, cyclopentane has significantly less strain, but then something weird happens, right? At 6-membered rings, cyclohexane, we have no ring strain. And then as we get further and further and bigger, right, we start actually losing our ring strain beyond about 14 carbons. And so what's going on here? What did they not think about in their hypothesis, right? So what did they kind of mess up or just not think about? Well, remember that cycloalkanes and all organic compounds in general aren't 2-dimensional, right? They are 3-dimensional. And so when you're looking at these polygon pictures right here, you're picturing them as 2-dimensional images. That's not how they are in real life. In real life, they take 3-dimensional, motifs that are different. And so we need to analyze their 3-dimensional structure and look at what kind of strain each one of these have. And so there's going to be 3 main types of strain. In cycloalkanes, right? The first one's going to be the one we just learned about, angle strain. And that's the strain from changing the angles. Second is going to be torsional strain. And this is the strain from overlapping bonds. It's actually a little bit more complicated than that, but that's what we're going to go with for now. And then there's steric strain. And steric strain is the strain from big things overlapping. And so These two last ones, torsional strain and steric strain, they're kind of very similar, and it's a little bit semantic-y, but they are technically different. So let's just take a quick look at the difference between the two. So in torsional strain, what we're talking about here is the bonds. So for example, if you had this eclipsed conformer, right, hydrogen is actually not that big. And so it's not a steric strain. You're not putting big things together. What's really happening is the repulsion from these bonds, or really is a little bit more complicated than that, but we're gonna go with this, right, due to overlapping bonds. And right, that's because hydrogen isn't big. Whereas if we take another look at a different Newman projection, where we have this methyl group here, and then we overlap it or eclipse it with another methyl group, this is now steric strain because methyl groups are big, but then we also have torsional strain as well from the bond angles, right? So this one would have both torsional and steric strain. So we'll analyze the three-dimensional shapes of some cycloalkanes and see what kind of strain they have.